So 4-1 is all about polynomial functions, and it starts off by just naming the different types and being able to identify what is and is not a polynomial. And we'll focus on what is not a polynomial in a second. But as you can tell, I have some vocabulary listed here as well as an example in standard form already. So let's define standard form. Standard form is a polynomial that is written from the largest exponent all the way to the smallest exponent. So we'll start with our larger ones and we'll go to our smaller. And it's important to notice exponent. It's important to notice right here that when we are writing this from largest exponent to smallest exponent, that we are ensuring that we are actually focusing on the exponents. Issues that I've had in the past are people really want to focus on the coefficients, when the coefficients is not actually relevant in this particular occasion. So we have to make sure that we are actually focusing on our exponents. So as we can tell, this function right here is already written in standard form. I've started with the exponent 3, then I go to the exponent 2, and then I go to the exponent 1, technically, because the understood exponent of just x is 1 when no exponent is shown. And then, of course, I have that plus 100. And if I wanted to get super technical, I could say that it does have a variable, but it's raised to the power of 0, if I really, really wanted to. But, we can focus that on that on a different day. The next vocabulary word that we need to make sure that we understand is the leading coefficient. Now, it's different than a normal coefficient. A normal coefficient is just going to be a number in front of a variable. In this particular case, we have a positive 1 or a negative 2 or a 5. Those are our coefficients. But a leading coefficient is going to be the first coefficient when written in standard form. All right, so as soon as we have our standard form, we can automatically identify our leading coefficient. So if we look over at our example, our leading coefficient is that first coefficient that we see, which is right here in front of this x. So I'll say this is my leading coefficient, and it's an understood 1, as I mentioned before. So I can say it equals 1, and I can even plug it into my function if I want to really very obviously see what this number is going to be. The third most important vocabulary word for this section is going to be your constant. And the constant is just a number that has no variable. Again, technically we could say that it does have a variable, but it's raised to the power of 0. But again, that's going to be like an honors thing. It's not really going to be a standard concept that's going to be required to be learned. And so we can say, all right, a number that has no variable, in this particular example here, the 100 at the very end is going to be my constant. It equals 100. And this is where our constants should always be. They should always be at the end. And then our final vocabulary word is going to be the degree of the polynomial. And obviously I didn't write that whole thing because I didn't have room. But the degree of the polynomial, this is going to be the highest degree of all of our terms. The highest degree of all of our terms. So if I look at my standard form again, the highest degree should be my first exponent. So I can see over here that this 3 is my degree. So if they ever ask me, well, what is the degree of the polynomial that we're working with, I can make sure it's in standard form, and then I can say the degree is equal to whatever. In this case, it's equal to 3. So in our instructions, our little example here at the bottom, it says in exercises 1 through 4, and we'll get to 3 and 4 in a second. It says decide whether the function is a polynomial function, and I'll explain that further as we experience it. If so, write it in standard form and state its degree, type, and leading coefficient. And I'm actually going to add to that the constant as well. Your homework may or may not include that, but it's always a good habit to, identify those key things. So the first thing I'm going to do is I'm actually going to write down my things. I need to find my standard form, my degree, and my leading coefficient. So I'm going to look at my function for number 1, and I can see everything looks normal. It looks very similar to the one that I just did, so I can say, yes, this is a polynomial. Standard form is going to be where I take all of my terms and I put them from highest exponent to lowest exponent. So my highest exponent is going to be this 4, so I'm going to write it as negative 3x to the 4th power. My next highest would be this 2, so it'd be plus 2x squared. The next one would be the x to the 1st power, which is plus 6x. And then, of course, my constant comes last. So that'll be a plus 1. Now it is easy to identify my degree of the polynomial and my leading coefficient. My degree is going to be that highest exponent right here, which is 4. And my leading coefficient is going to be that coefficient that comes first in standard form, which is now a negative 3. And then, of course, my constant is going to be the number that has no variables, and so that's going to equal 1. So then I can do the same process again for number 2. I'm going to go ahead and just put all the standard form, degree, leading coefficient, and I'll do my constant. And I'm going to look at this and I'm going to say, okay, well, m of x is equal to negative 3/7 x to the 3rd power. Okay, so even though I have a fraction, I've dealt with x to the 3rd power. That's not something new. But then the next part says plus 7 over x, and I haven't really dealt with this. And so I can actually stop here and say that because this portion is different, not because it's a fraction, but more of because my fraction has a variable in the denominator. That's very unusual. And since that occurs, what I'm going to say is this is actually not a polynomial. It is not a polynomial. And that is my answer. I don't have to do anything else. So anytime you see a variable in the denominator, not a variable next to a denominator or next to a fraction or decimals, that is irrelevant. We're solely focusing on the fact that the variable is in the denominator. Because of that, this is considered not a polynomial. So let's talk about the different types of polynomials for a second. When we have different classifications of items, we can separate them into, if you will, two different categories. We can focus on a polynomial as the number of terms, or we can focus on the type of polynomial that it will be based off its highest degree. So let's focus on each one separately. And these are things that you should have already experienced learning or practicing back in Algebra 1, but again, we're just sort of recapping all of this and putting it all together. So if we focus on how many terms we have, if we only have one term, let's say we have x, if we have one term, we would say that this is going to be a monomial, because mono stands for just one item. And so continue on with a sort of like English lesson, if you will. If I have two terms, x plus 4, that is going to be a binomial. Bi meaning two, binomial. All right, and then if we have 3, well, it's like a tricycle or a tripod. It has 3 legs or 3 wheels. And so a 3-termed polynomial is going to be called a trinomial. And anything beyond this trinomial is going to be considered a polynomial, because a polynomial is just a general term for all of this. So if I wanted to, I could say that a monomial is a type of polynomial. Polynomial is everything. Monomial is just specific, along with binomial and trinomial. Those are specific. Polynomial is the general term. And since we don't have specific names for a polynomial with 4 terms or 5 or 6 or 7 terms, we would just generally call that a polynomial. So after we determine, okay, this is a monomial, binomial, trinomial, then we can focus on the degrees. So if our highest degree is 0, well, remember, if our highest degree is 0, then technically we don't really have a variable, and so really that's just going to be a constant. This is going to be a constant. So like back in algebra 1, this would be like x equals 4 or y equals 5. And so that was just a straight up and down line or a straight flat line. It was a constant. If our highest degree is 1, though, that'll be like y equals mx plus b. That particular formula has x inside of it, and the highest degree of that is x to the first power. That is a linear function. So we would say if it has a degree of 1, if the highest degree is 1, then it would be linear. In our last couple of sections, we've been working with quadratics. Quadratics' highest degree that it can go is 2. So if our highest degree is 2, it's going to be a quadratic, and that's going to be something along the lines of ax squared plus bx plus c, or even something like in vertex form when we had a times x minus h squared plus k. Some polynomials that we haven't really experienced yet, and we probably won't spend a lot of time with, to be honest, is when our degree is 3 or 4. If it is 3, then it's going to be obviously x to the third power, and that is going to be cubic. If it is 4, it's going to be quartic. So now when we go back to answering those questions 1 through 4, we can answer it a little bit further. We can say, okay, it's a monomial or binomial or trinomial or polynomial, and then we can take it a step further and say, what type is it? Is it a constant? Is it linear, quadratic, cubic, or quartic? So let's do number 3 and 4. So numbers 3 and 4, we continue on, except we're adding on those types of polynomials of if it's a constant or linear, quadratic, cubic, quartic. So first things first, we're determining if it's going to be a polynomial. Remember, we're looking for things that are very, very strange. So for example, in number 3, we have the square root of 15 times x. And so if you look very carefully, you can see that the square root only extends over the 15. It doesn't extend over the x. And so thankfully that helps avoid any sort of complicated occurrence that might happen here. And so this is actually going to be considered a polynomial. We'll say, yes, it is a polynomial. In standard form, we put our highest exponent first, which is actually, it's already in standard form, so we're just going to copy this down. And I'm going to separate that square root of 15 and x a little bit just to, so we can see very easily that the x is not under the square root. If I look at this, my degree, I don't see it on the x, so it's an understood 1. And that means that this type is going to be a constant according to my notes. This is going to be a constant function. And my leading coefficient, even though it's sort of a complicated number, I'm just going to carry it down anyway. It should be the square root of 15. So then number 4, same idea. We're looking for anything that's super out of place, and we can see that there is not. So we are going to say, yes, it is a polynomial. And when we write it in standard form, we have x squared that's going to come first, and we're going to take the whole piece and put it first. So it's going to say negative 2x squared. And then I'm going to move on to my next piece, which is going to be that positive 3x. And then I'm going to finish it up with the constant, which is negative 2 times the square root of 3. From here, I can say that my degree is going to be 2. That means that it is a quadratic function. And its leading coefficient is going to be a negative 2. So it is a good idea to have a little list of things that are not polynomials so that the next time you see it, you know for sure you don't even have to do anything, because as we did in number 2, when we had the degree or the variable, in the denominator, it was very obvious, or it will become very obvious that that is not a polynomial, and we don't have to do any work for it. So there are three main things you're looking for. You're looking for, again, if we have a variable in the denominator, or if we have a power of -1, so let's say we had x to the power of -1, because in reality, these two items are equivalent. We'll learn about that later, but for now, just know that if you see in the denominator or to the power of a negative, we know that it is not considered a polynomial. Or we could also have the variable be an exponent, which is something that we haven't dealt with either. So that would be something like, let's say we had 1 to the x power. This is going to be all of our instances of what is not considered a polynomial. And to be honest, technically it's not going to be 1. It'll be anything besides 1. So let's say it's going to be a 2 to the x power. So anything like this is going to automatically classify it as not a polynomial. So in exercises 5 and 6, it says to evaluate the function for the given value of x. And so what we're going to do is we have our function h of x or g of x or whatever function they give us, and wherever it says x equals, we're going to take that value and plug it in to all of our x locations. So we have our x equals 2 right here. I'm going to plug it in to here, here, here. And I don't see any other x's, so we're just going to plug into those 3 places. Please make sure that when you're doing this, you use parentheses. All right, it is extremely important to use parentheses. If you do not, you will get the wrong answer. So for this particular example, we have that negative x to the 3rd power. Well, the negative is part of the formula, and I'm going to keep it outside of the parentheses, okay? Whatever I plug in that wasn't originally part of my problem, that value is going to have parentheses around it. So it's going to read as negative parenthesis 2 to the 3rd power minus 2 times parenthesis 2 parenthesis to the 2nd power. So all of the pieces that I'm plugging in are going to be inputted in with the parentheses. Everything that was already a part of the equation, the negative, the cubed, minus 2 squared, all of that is going to stay outside of my parentheses. Plus 4. All right, now that I've done this, now I'm just going to follow my PEMDAS order of operations. So first things first, I'm going to do my exponents. Please note the negative is not part of this at the beginning, so we're going to put it at the beginning and leave it alone while we work with the exponents. 2 to the 3rd power is 8 minus 2 times 2 squared, which is 4. And then the next part is multiplication, so I'm just going to hold off on that for a second. Now that I'm done with this, I'm going to do normal multiplication. You can think about that negative in front of the parentheses with 8 as a -1. -1 times 8 is going to give me -8. -2 times +4 also gives me -8. And -3 times 2 gives me a -6. And we carry down the +4. Then from here, I can say, all right, I can add these up. This is going to give me a -16. -6 plus 4 is going to give me a -2. So -16 plus a -2 is going to be a -18. All right, and so there's a couple of ways that I can write this. I can either leave the answer like this, saying this value when we input our x, our output is -18. But sometimes the textbook requires us to write it in a different format. They are basically going to take that beginning piece, that h of x, and they're going to show with that h of x what we inputted into our equation. In this particular case, we inputted a 2. So it would say h of 2 equals -18, where the 2 is our input and the -18 is our output. Again, not all of textbooks require this, but it is a very common practice, and every once in a while your textbook is going to throw this at you. It's also sometimes just going to say h parenthesis and then a blank that you can type values in. And so that's why I wanted to show you this format really quickly. So number 6 is very similar. We're using the same process, but again, I'm just want to stress the importance of ensuring that your input, whatever number you're plugging in, has to have parentheses. So -6 starts off with x to the 4th. So I'm going to replace the x portion, okay, all these x portions, with -4. Notice it is in parentheses. -32 times, with the parenthesis, -4 squared. Plus that 256. I'm going to work on my exponents first. When you're typing this into your calculator, please make sure you double check 2 things. First of all, it needs to be in parentheses. Can't stress that enough. And then number 2, you need to make sure that you are using the correct sign. This does not say a -4. Minus means that there's a number in front. There is no number in front currently. This is multiplication. So because we're talking about multiplication, we have to use the correct minus sign on the calculator. Typically, it is going to be the minus sign with parentheses. This particular button on your calculator is specifically dedicated to being the negative. Okay, so we would say parenthesis, -4, parenthesis, all of that to the 4th power. That's how we get a positive 256. Moving on. -32 times -4 to the 2nd power, which is going to be 16, positive 16, and then carry down that plus 256. One last thing we need to do, and that is multiply our middle values here, which is going to give us a -512. We can plug this entire line into our calculator at this point, and we should get 0. If I want to continue on and put it in the format that you may or may not see on your homework, then we are going to say this is going to be g of, or h of, it doesn't really matter. We inputted our -4, and we got an output of 0. Another way to think about this is to say that when x is -4, our y value, again our output, was 0. So the last concept of 4-1 is something called end behavior. And this is just a generally good idea to sort of have a basic understanding of. It's not something that I'm going to be explicitly testing you on, similar to some other concepts that I've said before. Yes, we're going to use this for like homework, but it's not really going to be something I test you over. However, I do know that they do test this in our county. So if you are thinking you might be leaving our school, this is definitely something that you should memorize because it is expected to be known in other schools. Again, however, it is a really good idea to have a basic understanding of what is occurring. So end behavior is just talking about the different sides of your picture. If you were to graph this, what does it look like? Well, since we've been talking about the degree and the leading coefficient, that is actually our sort of markers to determine what sort of shapes are going to occur. And in other schools and maybe in like a pre-calculus class, I would spend more time on the end behavior and try to get an idea of what is happening and things like that. But in this particular case, I'm not too worried about it, so we're just going to go over the basic ideas. And the basic ideas are, well, if your degree is odd and your leading coefficient is positive, all right, and this is something that we have dealt with before in like Algebra 1. So let's say it's something like, well, 1x plus 1, okay? We've had this before. This would be a y-intercept of 1 with a slope of 1. So it would start off on the bottom left and go to the top right like this. So it could be as simple as this, or I could have something even more complicated. Let's say I could have something like this. Yeah, perfect. And so what's important to know about this is that the reason why this is still part of this, I guess you could say, family, is because, remember, the degree is odd. And a good way to figure this out is look at the number of turns that happen in our picture. So, for example, I start off in my graph, or my more complicated squiggle, if you will. We go up, we start off going in this direction. This is sort of our 1, and then we start going down 2, and then we go up again, which is 3. And so because I am changing direction like a roller coaster here, 1, 2, 3, I can look at this picture and automatically know that the degree of this squiggle is in fact 3, because I have 3 different directions I'm going. I'm going up and then down and then up. So again, this is our end behavior. So even though I can determine this is 1 to a degree of 3, what I care about is this end and this end, okay? And since I care about this end, there is a statement that we can write no matter what based on our polynomial having an odd degree and a positive leading coefficient. And that particular statement is, as x is approaching infinity, okay, and that's when it's approaching or going on the right hand side, f of x is going to be approaching infinity as well. So let's go back just a little bit so that I can talk about that first statement really fast. So as x is approaching infinity, f of x is approaching infinity. So x obviously is going to be the x-axis over here, and as it's approaching positive infinity, as it is moving from the origin to the right, we see that what's happening to our y values, well, they're going up. See, as I'm moving this way, I can see at this point it just shoots up, okay? And so that's what that first statement means. So then my second statement of this section is, as x is approaching negative infinity or moving towards the left, all right, what happens to my function? Okay, so from the origin, I'm moving to the left and I see it just drops down. So it is dropping down towards our negative numbers. So we would say the function, or f of x, approaches negative infinity. Okay, so this is where a statement comes from. And so when you're given a polynomial, after you put it in standard form, identify your degree and your leading coefficient, you can write this statement based off of those two things without even graphing it or without even looking up what the function looks like on a graphing calculator. So the next box over to the right, same idea. We're going to continue on with, let's say, a degree. We'll keep the degree odd, and we'll say that the leading coefficient is now negative. So if we were to make it similar to our linear function, which is something we've already dealt with, it would start in the top left-hand corner and go downwards, like as you can see right here. And if I wanted to make it more complicated, let's say instead of having a degree of 1, we go up to the next odd degree, which is 3, it would look like this. All right, and so I'm going to write my statement, except now things are a little bit changed. But it's important to know that the first part of our phrase is typically not going to change. So as x is approaching infinity, as it is moving to the right, remember. Okay, there we go. As x is approaching infinity, it's moving to the right, my values are shooting downwards. They're going towards negative. So we would say, as x approaches infinity, that part hasn't changed, f of x is approaching my negative numbers, or negative infinity. All right, so that portion has changed. So again, the first half doesn't change at all. The second half is going to change depending on your type of degree and your leading coefficient. So then if my function, or if x is approaching negative infinity, well, now as I move this way, my values are shooting up towards the positive. So I would say, as x approaches negative infinity, f of x approaches positive infinity. All right, and so now we can move on to that next one. Let's go diagonally bottom to that bottom left-hand box. This one will change it to the degrees even, and our leading coefficient is positive again. So this would be something like a quadratic function like this, because that's our first sort of anything. Obviously x is 0, that's not even, that's just 0. So the first even number that we have is 2. So x squared would be a parabola like this. But again, it could be as complicated as the next one. We could say it could be x to the 4th. So it would be a picture that looks like this. And again, we can determine what the degree is by looking at our functions. We can say, okay, well, this function starts off going down, that's one direction, then going up, that's two different directions, then going down again, that's three, and then going up again. So it changes directions 4 times, which is our degree. We would say this has a degree of 4. I mean, we could even put even more squiggles in between our end behavior or our end between our sides, and we could have 6 or 8 or whatever. I mean, it would look a little weird, but we could do it. And so we can make our statement. Again, that first half doesn't change as x approaches positive infinity. Okay, so let's look at our picture. As x approaches positive infinity, our line goes up towards the positive number. So we would say f of x approaches positive infinity. Okay, then the next part, again, that first half hasn't changed. As x approaches negative infinity, okay, again, that's the left-hand side of our graph here, from the origin, as it is moving to the left, what is our graph doing? It is shooting upward again. So as x is approaching negative infinity, f of x is also approaching, or it should say positive infinity. Should change that. It should say positive infinity right there. Let me just fix that. There we go. There we go. All right, so as x approaches negative infinity, as it moves towards the left, the y values, f of x, approaches positive infinity. And so then our last piece is going to be when our degree is even, but our leading coefficient is negative. So this is when our pictures just start facing downwards. Again, our function, our statements are going to start off the same. We'll say it's as x is approaching positive infinity. I'll look here. I see as it's moving to the right, my values are going downwards. I can see the arrows are pointing down. So we would say f of x approaches negative numbers or negative infinity. And then as x approaches negative infinity, again, look at our picture. Here we are moving this way. Again, it is still moving downwards. We would say f of x is still approaching negative infinity. So having a 3x5 card when you're doing your homework that helps you organize all of your material and organize your thoughts are going to be extremely helpful when it comes to your end behavior. I know that it seems really complicated, but as long as you have that 3x5 card that keeps your information organized, you should be okay, and you shouldn't have to worry about mixing up your statements, because again, it's not going to be something that I require you to memorize. It's just something that you will have to do on the homework, which you will have your notes for. So for our exercises 7 and 8, it says to describe the end behavior of the graph of the function. So we're going to have to use our statements. And so before we do our statements, I'm going to just summarize what my statements are going to say. Now, I don't have a 3x5 card in front of me, so I'm just going to do this from memory. And so I'm going to say, all right, this is going to be odd and positive, and then we can have even and positive, odd and negative, or even and negative. All right, and the statements, if I were to draw the pictures, these pictures would look like this. This one would be the opposite of that. If it's even and positive, that would be like a parabola going upward. And then if it's even and negative, it's a parabola going downward. All right, and now that I have like a little picture, I can sort of see what's happening. And I can say, well, for my odd degree with a positive leading coefficient, it looks like on the right-hand side, so on the right-hand side, it's when x is approaching, you know what, I don't know, let's just do right is on the, if it's on the right-hand side, it's moving upward, and if it's on the left-hand side, it's going to be going downward. Okay, so then on my other picture, it's reversed. On the right-hand side, it's moving downward, and on the left-hand side, it is going upward. All right, for my even value, or for my even degree with a positive leading coefficient, again, I have my picture off to the right there. I know it looks like event, but I promise you it's even and then positive. But on the right hand side, it's going upward, but because it's symmetrical, so the same thing is happening on the left-hand side. The left-hand side is also going up. And whenever we flip it or we have a reflection occurring, well, now it's going to be the right is going downward. And of course, since it's still symmetrical, the left is also going downward. All right, so I just took my sentences that I had earlier, I just summarized them in sort of like layman's terms instead of having those particular statements. But when I answer the question, I am going to have to use those specific sentences. But I did want to just summarize what they meant for a second. So number 7, everything is in standard form, so I can just go ahead and find my highest degree, which is going to be 6. And my leading coefficient is going to be a -3. So my sentence here, let's see, if I look at my layman's terms that I've sort of written down here at the bottom, my degree is even, and my leading coefficient is negative, which is going to be this sentence right here, which of course I'm going to fix and make it mathematically correct. All right, so I can get rid of that. And so now it's going to say, my description of this end behavior is going to say, well, as x approaches infinity, that's on the right-hand side, my function is going downwards or towards negative infinity. And then as x is approaching negative infinity, this is when it's on the left-hand side, it is still moving downwards because it's, again, symmetrical. So it would be approaching negative infinity. And if I wanted to draw this picture, I could say, all right, well, it's going to be something like this, okay? And the only reason I know it's going to be something like this is because I just sort of counted it really fast, but I'll show you what I did. With my first sort of direction, this is going to be 1, and then I turn and I go downwards, so that's 2, and then I turn and go upwards again, that's 3, I turn and go downwards again, that's 4, I turn and go upwards again, which is 5, and then I finally turn and go downwards, which is 6. So I'm just showing you that I can sort of sketch out what my picture is kind of going to look like. I'm not saying that this is exactly what it looks like. I'm just sort of getting a sketch, an idea of what is happening, but this is how you would sketch it out, okay? So let's put a separation to do number 8. My degree, currently things are out of order, so if you notice, my highest degree is actually 5, and therefore my leading coefficient is 3. So if I were to look down at my little cheat sheet that I've written here at the bottom, my degree is odd, and my leading coefficient is positive. So it's going to be this sort of statement or this sort of scenario that occurs here. So my sentence is going to be, as x approaches infinity, as it's on the right-hand side, my function is going to be moving upwards. It's going to be towards positive infinity. However, when it's on the left-hand side or approaching negative infinity, the function is moving downwards or towards negative infinity. And remember, these are our answers. So if I wanted to draw the picture for this, all right, here's my coordinate plane. I know that it's going to look something like this picture right here. So I'm going to start down, and I'm going to go, let's see, 1, 2, 3, 4, 5. Okay, so I think I got it there. Let's just double check. It should be 1, 2, 3, 4, and then 5. Okay, so yes, I did do it correctly. Again, it's not going to be exact. It's just a general idea of what is happening. But this is our picture of what it should vaguely look like. The final example we're going to do is when we do the opposite, or when we approach it from sort of an opposite direction. So instead of looking at our equation first, we're actually going to look at the graph first. So let's clear this and get that up. So here is our final question from this section. It says, describe the degree and the leading coefficient of the polynomial function using the graph. And so we're going to approach it as the same way as we've been working. We have our function here, and so to determine our degree, we are going to count how many turns it makes. So originally, it starts off with 1, and then it moves to 2, and then it moves to 3. So I can say with confidence that this degree is going to be odd, or it's going to be equal to 3. But for now I'm going to say it's odd because the function or the polynomial makes 3 turns. Okay. And so I feel like we've practiced that plenty of times already, that is not super hard to understand. So then the second part is, well, what is our leading coefficient, or what type of number is our leading coefficient? So from here I can say, well, remember how in Algebra 1 you guys learned to determine if a linear function was positive or negative, and you determined that by reading the graph like a book from left to right. Okay, there we go. All right, so we read our graph from left to right. So as we're moving from left to right, we can see that its final turn is going downwards. And because its final turn is going downwards, we know that this is actually going to be the leading coefficient is going to be negative. Again, because our polynomial moves downward as we go from left to right. And so we can even sort of draw a linear function to help us see that movement there. But that is our entire section for 4-1. Please make sure you're doing your homework. And if you have any questions, please contact me on Remind.